All right, let's get started. Okay, good morning and welcome to E141, lecture 13. So let me begin by taking any questions you may have from last time about lectures, class material in general, comments, suggestions, anything. Okay, so let me first give you a couple hints about your next homework and also some background information that you'll need for the project. We will put projects online by Saturday 5 p.m. and some of the problems there will actually help you solve one of the homework problems that we actually purposely gave this week to help you get started and get thinking about the project. So online we will post a couple things. Basically we'll post some tips and background material. So we'll post some tips that you would need to do some HSpice simulations and some background material that you would need to get better started on your project. What we are going to do for the project is some sort of a general buffer tree. And you will need to do a couple things. First of all, you will have to find optimal sizing, which is what you've been doing in the past couple lectures. And then you will have to basically verify how does these numbers correspond to your SPICE simulation. So you'll be really having the ability to sort of verify the accuracy of these simple models for hand calculations. And then from there, you will have phase number 2, which would be basically, now let's assume that we no longer have minimum delay, but we can tolerate maybe 5 or 10% delay penalty. So now the question would be then, for this general type of buffer tree, how do you pick optimal sizes to minimize power consumption? And you would have to verify that in SPICE again. And that would be basically the task for your project. But to get you started, let me give you a couple pointers that would be useful for homework and then also for the project later. So for in the homework, we will give you some problem of this kind, basically. So you will have something of this nature. So you have large load capacitance and you have first stage that is unit sized, and then what you need to determine is the size of the second and the third stage such that you have certain goal satisfied. For example, minimum delay. That's the good starting point. And then you also have some branching over here at the output of the first stage and branching at the output of the second stage. And this comes from the fact basically that when you build a clock tree, you build it in a sort of hierarchical way. So you basically have this unit-sized inverter, and that guy branches off to a certain number of domains. So now the size of all of these is x, x, x. And then you further distribute each of these basically to your clock subdomains. And the size of each of these is y then. So this factor over here that represents the number of these parallel branches is what we call the branching factor. And we will come to that on Tuesday when we explain logical effort and introduce these concepts. But what you need to really do in this case to minimize the propagation delay, you have to take your overall fan out that would be equal to the load capacitance divided by the input capacitance of the first stage times the overall branching factor. So you will have B1, B2. And then you figure out your optimum fan out per stage would be third root of this capital F. And then you can basically work backwards through the chain to figure out your x and y. So basically your y would be equal to CL divided by F. And then you have also this branching factor in play. So let's see, then you have x is equal to B2 So basically you have the effective load over here would be B1x. That would be the delay of your first stage. So you have 1 plus B1x for the first stage. Then you have B2y divided by x, 1 plus that for the second stage. And finally for the third stage you have 1 plus CL divided by y. And then you have to balance each of these terms, B1x, B2y over x, and CL over y. And that's how you figure out then the optimal sizes. So then the next thing will be to validate this in HSpice. And in order to do so, you will need to have estimate of TP0 and gamma. And in the posting that we will have online on Tuesday, you will have clearly outlined methodology along with the SPICE deck, how you are going to estimate TP0 and gamma. And you can use, for the homework problem that we will post today, you can either do it by yourself, calibrate your TP0 and gamma for our technology, or you can just wait until Saturday and then sort of understand the methodology and use that number that will be given in the hints and tips. So for for the SPICE verification, what we normally did so far in the lectures for the hand analysis, which was perfectly valid to do, to just sort of get the first order estimates of the important parameters that influence our delay. So we normally assume step function at the input, but that is unrealistic in your real circuits. And I think some of you actually pointed some pretty good questions from the lab when you try to simulate basically your unloaded inverter, extracted and also loaded with 50 femtofarads, and you were trying to do sort of estimate the intrinsic capacitance by measuring the delay of an unloaded case and the delay of a fully loaded case. And then you ended up with something that was pretty unbelievable. For example, that the intrinsic capacitance was about 50 femtofarads. But what you had actually, if you apply the step response over here, so you remember from a couple of slides back, due to the capacitive feed-through, you have basically overshoot in the case of unloaded gate, and when it's heavily loaded, you have much less of that effect. And basically, when you calculate the delay of the unloaded case, you actually don't calculate this delay, which is what you would expect, but your delay gets longer because of this overshoot problem. And that exactly comes from this slope problem. So to create a realistic environment for your HSpice simulations and to sort of simulate the real world environment, what you need to do is basically add a couple stages to the input that will shape up your signal slopes. So what you would do basically over here, just add maybe 2 buffers. That would be enough. And then you can drive this with the ideal slope at the input, the ideal step function. So over here, you have basically 1, 1, and 1. So you would have pretty realistic input waveform slope for your delay analysis. And that's what you're going to be using for SPICE verification in your homework and also later on for the project, just to make sure that you have a realistic driver for your input gate. And also hint, you will see that more in the document that we will post. It's all useful to use the sub-circuit command over here in HSpice to replicate all of these inverters. So you basically create one inverter with parameterizable WP and WN, and you just apply scaling factor to sort of get these inverters with a larger size. Okay? So now let's go back to... Everybody clear a bit about this? Makes sense? All right. Great. So let's now go briefly to slides. So today we are going to continue with CMOS Logic, and we are finally at the stage where we can do some fun and interesting things and get to the core of the E141 material, the ways we implement Boolean functions, and later on build that upward in the hierarchy for more useful operands like adders and multipliers. So projects will be posted on Saturday, 5 p.m., and you will have about 2 weeks. They'll be due Monday, October 31st at 5 p.m. Homework 5 is due today. There'll be homework 6 also for the next week, and then week after that we don't have homework, and hardware lab is next week. So today we are going to talk about first introduce static complementary CMOS circuits, then talk about physical realization of these functions, and finally go into the delay analysis to understand the performance of these gates. So this is what we started last time. So basically we distinguish between two types of logic implementation. So we have combinational logic circuits and we have sequential logic circuits. So in essence, combinational logic circuit basically just implements a certain Boolean function at the output at any given point in time, excluding transients. You have that your output is some function of your input vectors. And sequence of input vectors doesn't matter. You always have sort of one-to-one mapping between your input vectors into your output result. Sequential circuits, on the other hand, have output that depends on input vectors and also previous states. So it has a memory, basically. And your inputs are, the states are basically taken as outputs from your circuit and fed back to the input. So in this case, it really does matter in which order you apply your input vectors. And good examples of such sequential circuits are, for example, counters, where you have basically count relative to the previous value, then oscillators, memories, and so on. And we will come to these circuits later in the class. But for the time being, we will first figure out these combinational logic designs. Question?
For sequential logic, should this output be a function of previous output or previous input?
That's a good question. It depends really how do you look at it. So you can basically say that this is really a function of all the inputs that are fed back from the output. But in essence, these inputs are generated by taking some of the outputs from your network. So you can basically argue either way, but this is basically just the convention that we use that say it's a function of current values of the input and the previous values of the input or the output, either way. But you basically just have this concept of memory, of a state. Say we have certain block that has some memory in there that also influences the output as well as the incoming inputs. So these are some of the properties of static CMOS circuits that we are quite familiar with at this point in time. So very important point is that at every point in time, each gate output is connected to either VSS or VDD through a low resistive path, because we have a pull-down network pulling down to ground, or we have a pull-up network that implements logic 1 that's pulling up to VDD. So we have low impedance nodes and states defined through pull-up or pull-down network. So the way now we implement these functions is, so basically every function can have some inputs, 1 and so on in K. And then the way we realize certain logic function in hardware is through these pull-up and pull-down logic networks. So you have pull-up network, and then we have pull-down network. And all these inputs are feeding into in 1, in K, in K. So for every time when your function has a value of 0, then basically your pull-down network is pulling down the output to ground and implements this logic 0. Also, for the cases of input vectors where the function has output 1, then this pull-up network is pulling up to VDD and implements that logic 1. So important features of these pull-up and pull-down networks are that they are dual logic networks, in a sense that they basically implement the same function, but just the pull-down network covers all the cases where output is equal to 0, and pull-up network covers all the cases where output is equal to 1. And also another important feature is that pull-up and pull-down networks are complementary. What this means is basically that they implement the same function but just in a complementary way. One logic networks implements all the ones, the other logic network implements all the zeros. So that's basically the basic concept for static complementary CMOS gates. So now let's see how we can realize these pull-up and pull-down networks in practice using transistors, and see what kind of logic operations we can perform using various configurations of transistors. So in order to realize a pull-up and pull-down network, let's first review some of the basic switching properties of MOS transistors. So we basically have two types of transistors we can use. We have NMOS, that is turned on when its gate input is high. And when NMOS is turned on, then it simply provides a conductive path between the source and drain. And then you can say when A is equal to high, Y is equal to X. Basically, this NMOS propagates X from one end to Y to the other end, connects drain and source. And that way it implements a logic function. On the other hand, we have a PMOS device that is active when its gate signal is low. And this is this inverting bubble, basically. That's a standard convention that you basically label active low signal. So this means when this signal A is low, then this PMOS is on, and then you have Y is equal to X when A is equal to low. Now, a couple things that we also need to keep in mind. We need to know, refresh that NMOS conducts strong logic 0, and weak logic 1, and PMOS conducts strong logic 1 and weak logic 0. And you remember this because we have basically, if you assume that X is high and A is high, then you can't reach higher than VDD minus VT over here. You have the threshold voltage drop from the NMOS. But when X is ground, then Y pulls down all the way to ground. So that's basically two fundamental things that we need to start from. PMOS is active low, NMOS is active high, and NMOS conducts passive strong logic 0, and PMOS passive strong logic 1. So let's now see what kind of configurations we can use these two devices in to implement some of the logic functions. So we basically distinguish between two basic principles. So we can have a serial connection of transistors, or we can have a parallel combination of transistors. So let's look at the case of NMOS first. So in this case, Y becomes X only if both of these transistors are turned on, because that's the only case where you can basically provide conductive path between drain and source of transistor controlled with gate signal A, and then further drain and source of transistor controlled with the gate signal B. So you have Y is equal to X only if A and B are both turned on. Okay? Then in this case, either of the two can be turned on to provide conductive path between X and Y. So you have Y is equal to X if A or B. So basically you see that NMOS, serial combination of NMOS transistors implements AND function, and parallel combination of NMOS transistors implements OR function. So now let's see what happens if we do the same for the PMOS. So let's consider a case of PMOS. So we have again A and B, X. So now Y is equal to X also in the case if both of these transistors are turned on. And they happen to be turned on only if A bar is true, when A is low, and B bar is true, which is actually a NOR combination of inputs A and B. And then you have parallel configuration of PMOS, where you have y is equal to x if A bar or B bar, so that is equal to A, B complement. So basically what you have, that this is a AND function, this is OR, this is NOR, and this is finally NAND. Okay. So now we can also consider a case basically when PMOS transistors implement pull down and NMOS transistors implement pull up. And what's going to happen in that case, basically if we have, let's go back to slides actually over here. I have it illustrated over here. So basically when you have a pull up with a PMOS transistor, then we know that PMOS is really a good pull up device. Basically when the gate is low, so this signal turns on the PMOS, then you can get rail-to-rail swing. So you can basically pull up this output from 0 to VDD. In the case when you have NMOS transistor as a pull-up, then you have to have VDD at the gate to have it fully turned on. So you have a logic 1 to turn on this transistor, and then you have output going from 0 to VDD minus VT. So you have actually a threshold voltage drop over here. Similar case occurs for the pull-down network when it's implemented with the PMOS. You basically have pull down from VDD down to only VTP because of the threshold drop over here.
Why would you want to do that? Would that be good for power? Or?
Exactly, that's a very good point. That's what I was actually just leading this into. Basically, reduced swing gives you very good properties in terms of power consumption, because we know that power is proportional to the voltage swing on the capacitor. But then the problem with this basically would be what will happen to the propagation delay of the next stage if you have reduced swing? It keeps increasing, right? Because you don't have sufficient drive strength to strongly turn on the transistors in the next stage, and therefore it's sort of a trade-off. You can have basically lower power, but you have to pay penalty in performance. So the pull-up and pull-down networks are dual in a sense that basically we can show here using this De Morgan's theorem that you have basically NOR function is equal to the N function of complementary inputs, and also NAND function is an OR with complementary inputs. So very important concept also to understand is that the complementary CMOS gate is always inverting. So you can either implement NAND or NOR. If you need to implement a non-inverting gate like AND or OR, you have to add extra buffer inverter stage at the output. So let's do now one example over here. So let's go over here to do implementation of a NAND gate. So for NAND, we know that we can have, so let's do 2-input NAND. So our A and B can be 0, 0, 0, 1, 1, 0, or 1, 1. So output is 1 only if both inputs are 1. And otherwise output is false is if either of the logic signals is false at logic 0. Oh, that's correct. This is AND. and this should be flipped. This is AND. Thank you. And this is NAND. All right. I was just checking if you were sleeping. Just checking. Okay. So this is output of a NAND. So you have 1, 1, 1, and 0. But you actually just raised a good point. So we now know that AND series combination of AND transistors implements basically series connection of two NMOS transistors implements AND function. But now, since we are pulling down to 0, we are actually implementing a complementary function with that pull-down network. So we're implementing a NAND. So basically, in this case, when both of these transistors are turned on, so we have the following case. So this is the pull-down. We say that output is always implemented as 0 using the pull-down network. So we have A and we have B. So we have ground. So this is now pull-down network. So out is equal to 0 when both A and B are equal to 0. And now when either of the two inputs is equal to 0, we have situation when output is equal to 1. So that is our pull-up network. So now from the De Morgan theorem, we know that NAND function is implemented as a parallel combination, which is basically OR with inverted inputs. So you have basically A and B that are octave low in this case. And then you have VDD. So for the pull down, this is pull down network. Basically we have that out is equal to AB. So that is a conduction to ground. And for the pull-up network, we have that the function is equal to A bar or B bar, because A low or B low activates either of the two parallel branches. And that is actually A times B bar. So this is now conduction to VDD. So this is also actually A times B because we are taking complementary output. So let's say if G is an AND and F is a NAND, then you have basically G of input 1, input 2, and so on is equal to F of all these complementary in 1. This is basically what this tells you is just to use the Morgan principle over here to construct equivalent PMOS network. So now let's go back to slides. So that's basically the way you construct a NAND logic function. So similar analysis can be done for a NOR gate, where you basically have now that truth table looks different, and output is equal to 1 only when both A and B are equal to 0. Otherwise, it's equal to 0. So what this means is basically that the pull-up network, which needs to be implemented with PMOS transistors, this means that these two have to be in serial combination, and therefore the pull-down network needs to be the parallel combination of the two, because output is equal to 0 if either A or B are equal to 1, or both. Okay? Does this make sense? So now let's have a situation of this more complex logic gate. How would you construct, for example, a logic function like this? If you have output is equal to D plus A times B plus C, and that inverted. So what you know basically is that AND is a serial combination of NMOS transistors. So let's now first implement the pull down. So we know that two fundamental principles here. AND is a serial combination or is a parallel combination. And since we are passing logic 0, that's why we have this complement over here. So basically we have A, and then we have this in series with this term, which is a parallel combination of these two, right? So we have B and we have C. And also, in addition to that, we have this we now have implemented this term over here. Okay? And now we have finally D that goes in parallel with this. So let's say this is ground and this is node X. So now once you have a pull-down network, you can use basically this duality principle to easily construct a pull-up network. And I will show you one method that is very useful that you can use to basically automatically transform your pull-down into your pull-up network. And for that we will use graph theory. Everybody's heard about graphs. So it's basically you have nodes and edges that represent transistors in this case. So basically let's create an equivalent graph for this circuit over here. So we have, let's do this with other color. So let's say pull down is blue, and we have a blue graph over here. So we have a node X, and we have ground over here. So basically, let's assume that we have a vertical pull-down network. And all we need to do is basically to find equivalent representation of this circuit such that we can connect this X and ground depending on the topology of this circuit. And let's introduce one more intermediate node here and call it I. So basically what you do is step number 1, you label all the nodes in your circuit. And these nodes become nodes in your graph over here. And now you connect all these nodes using labeled edges that correspond to your gate signals. So basically, you connect X and I when your input signal A is active, which makes sense. Basically, you are connecting these two on a condition that A is high. And then you do the same thing for the other transistors. So you basically represent each transistor as an edge of this graph. So you have now signal B over here, and then you have C for this transistor, and then I finally need to connect these two, D. And this is my pull-down network. So now, in order to construct pull-up network, here's what I need to do. So for the pull-up network, I know that my pull-up network basically connects VDD and X, because my pull-up network is responsible for providing all the logic 1s at this X. So what I need to do is I'm going to put a pull-up network on top of this network, but now instead of going vertical, I'm going to do horizontal direction pull-up network. So, and then I can basically identify nodes VDD and X. So the second step I need to do is basically identify all these isolated regions, such as this one over here, basically. We have isolated region defined by these nodes I and ground and edges B and C. So I add a node to each of these isolated regions. Let me call this node J. And I have another node over here, which I call K. And now to construct a graph for the pull-up network, all I need to do is basically just connect all the nodes together, making sure that we cross each edge exactly once. Okay? So basically, if I connect X and K, I will cross this edge with signal D over here. So this would be one transistor in the pull-up network. So now if I connect, for example, my VDD, I have to connect it over here to K, and that goes to a transistor controlled by signal A. And then I also connect my VDD over here C, and finally connect these two nodes. This is B. Okay. And now using this graph, I can reconstruct my pull-up network. So what I know basically is, so here's my VDD over here. And then I know that I have PMOS transistors basically here. So I have parallel combination of A, and then I have serial combination of B and C. So this now goes to node K. So then I have a serial combination of B and C. And now this is my node J. That's the intermediate node. And then I finally have from node K to node X, I have another transistor that is controlled with this signal D. And I'm done. So that's basically a methodology you can reconstruct a complementary pull-up network. So now here's a question. What if I, for example, flipped X and VDD over here? I can do so, right? It doesn't change anything. So what would this actually mean to you then is basically that just these two sub-networks will be sort of, let's see, choose the appropriate color. So you would basically just have then D on top connecting to VDD, and then you will have this entire subnet on the bottom connecting to X.
Does it matter if you have the parallel combination of B and C above the transistor A? Because like by looking at the equation, like B plus A against the N and B plus C, right? So you can flip the order B plus C and A.
Correct.
So I mean, does it matter if you like have the parallel combination of B and C above the transistor A?
Correct. Correct. So basically, there is a number of solutions for this pull-up and pull-down network as well. And you can certainly flip, for example, B and C over here, reverse the order, or you can put D on top, as you pointed out. And we will come to that later when we do delay analysis. We will see that basically rearranging and ordering of these signals really does influence the delay. And in that case, that would be one of the techniques that you should be aware of as a designer. What would be the appropriate ordering of your signals to achieve the highest performance from your gate topology? But this is just a unified methodology that you can follow to construct a pull-up network.
Could you go over a little bit when you do the crossing, how to label the letters on the signals? Just because I don't know if it seems like if you draw the graph in maybe slightly different way, it seems like you could possibly I don't know. I just don't see exactly how to do it. So if you go from say from node K through say B and C instead of like having it cross A, then like how do you know that it would be A?
Okay, so the question is basically the methodology. How do you construct this graph and how do you label these signals, right? So basically, first, what you need to do is figure out this pull-down network, right? So you label all the nodes, and you need to connect all the nodes with edges that correspond to the controlled signals on the transistors, right? So you get that part. That's the blue graph. So you have X and I, you have A, between I and ground you have B or C, and for between X and ground you have D. Okay, and then second thing is you have to construct the pull-up network, equivalent pull-up network. So that's what you do by having this basically horizontal instead of vertical arrangement for the graph. And then for the pull-up network, you know that your pull-up has to connect VDD and X. So you just basically put two endpoints, VDD and X. And you can put them in any arbitrary order, as we just discussed. Basically, it will just change the sequence of your serially connected transistors. It will just change the order. Once you have figured out this VDD and X, you have to identify all these isolated regions that are basically enclosed with the edges of the graph and add nodes in there. So there will be additional nodes in your pull-up network. Once you do that, you just have some labels for those nodes, right? And then all you need to do is basically connect the graph from the PMOS such that each of these edges connects two nodes while intersecting with only one edge. So for example, this would be invalid connection. If you want to connect X and J, you can't do this because you are crossing both D and B, right? So in order to connect J, you have to basically connect over here to K, right? And then that's basically the strategy you follow. So each of the node connects through a transistor that has the same label as the edge that it's crossing over. So if this one crosses over D, then this will be my PMOS transistor controlled with D signal, and so on. Okay. So now let's go back to slides. So that's basically the methodology that we just explained. And now it's interesting to understand a little bit of practical realization issues with these gates. So when you go to any of the companies, you will find that the way they utilize all these basic gates like NANDs and NORs and so on, they have just a bunch of already predetermined cells that you can use in layout for your physical design. You have a whole library of NANDs and NORs and inverters and so on, so you don't need to redo them every single time. You don't need to do layout. So it's interesting to then understand some of the issues that are related with physical design, and this is something that we probably won't have a way to test on homeworks and exams, but it's really interesting to learn. So it's time to wake up now and have your attention for the next 10 minutes or so. There'll be something really interesting that you can learn. Very simple methodology that we can build on this graph theory to optimally construct our layout in terms of density and so on. So the way we implement these functions is using standard cells. And this is the standard cell layout methodology from the 80s. So what we had over here is a gate. And this is obviously, let's see, so we have pull down over here, and we have pull up over here. So we have transistors implemented horizontally. Can you recognize which gate is this? NAND gate, correct, because you have a serially connected NMOS transistors over here, and then you have parallel combination of PMOS. So this is one PMOS connecting VDD and the intermediate node, the output, and this is another PMOS transistor, and then you have ground, one NMOS, another NMOS connecting to the output of a function. And then you have an inverter over here. So the way this layout methodology worked in the 80s, you would basically have a routing channel above your VDD and ground lines. And then you would connect output of your standard cell over here to the input of the next standard cell. And you would have these poly lines extending over to this routing channel, which was allocated for routing signals between the standard cells. And as you can see, this is not really the highest density approach, because when you put a lot of these cells together, then you have a lot of this empty space that is basically allocated just for wires. And and then you would basically route your signals in the cell in probably metal 1, eventually metal 2 for VDD and ground, and then you would connect these cells together. In most cases, you would have isolated wells for example, N well for the PMOS for each of the standard cells, and that wouldn't give you really the greatest layout density. So people changed the strategy moving forward into the 90s, and that's basically the strategy of today. So the major change is you no longer have routing channels, but what you have is you have a standard height for your standard cell. So all of your standard cells have exactly the same height. And what that gives you is, if you go to the overhead camera for a second, so basically the way you would implement your function is, if I know that my standard cells are all the same height, I would just basically create a rows of standard cells, and then I would put them right next to each other. So this is, for example, my inverter. If I need to implement a little bit more complex gates like NANDs and NORs, then I would need to put more transistors in, and my standard cells will be a little bit wider, but they will be still the same height. You just keep the same height, and this would be, for example, a NAND, another inverter, and so on. And then you just connect all these cells using the routing at the top level, routing methodology. And then another thing that is also interesting over here is that for the standard cells, we have a convention that VDD and ground go with a certain specified width, and all these cells have the same height. And this is, for example, your ground, and then this is your VDD. So now the next thing you do when you route these rows below, you basically mirror the cells. You flip them over. So what you have is then another ground over here, and then you have VDD over here. And this way you can really achieve the high packing density. You can basically abut cells next to each other without even a need to connect these ground and VDD, as you will see in illustration in a second. So it's basically already, the cells are already pre-made in such a way that you just put them next to each other. VDDs and grounds are all connected. You have nice density, and even you have basically in let's go back to slides for a second. So even if you have, for example, transistors implemented, for example, a pull-up network over here for the N well, you can extend that N well all the way to the boundary of the cell, such that when you put together the next cell, all these diffusion areas will be continuous, basically. You have just one nice piece of diffusion, and you have really extremely high density. And then I will show you how you can utilize this graph-based approach to construct cells of highest density. Question?
Mirroring this diagram where the output of the first NAND gate should go to gate of the inverter instead of output?
Should it go to gate of inverter instead of output? I think, let me see, if this is VDD, that is correct. That's correct. Thank you. Yeah. So everybody got the point? Okay, good. Yeah, again, just checking if you're following. I'll fix the slides, thanks. Okay, so this is the way the standard cells are made. And this is a simple, let's see, this is an inverter, right? So this is what you're familiar with, a simple PMOS and NMOS. And the way this works is basically you have a fixed height for the standard cell. And typically, cell height is 12 metal tracks. And the metal track is the width of the metal, which is also called the pitch, which is repetitive distance between the two objects. You basically have, normally it's the case in lower level metals, that you have the same width of the metal and the same distance between the two objects on the same metal layer. So you have then your rails over here, then you have N well for the PMOS, and the cell height is about 12 metal tracks, and each metal track is about 6 lambda. So now in our technology, that is 0.75 times 12, so it's about 9 microns height for the standard cells. And now you see all these contacts, for example, to VDD. So when you flip over the mirrored cell and put it next to each other, you will basically exactly put the wells next to each other. You will have all these shared contacts, and basically everything nicely fits together. So that's the strategy, to try to sort of make this cell in a way that is really useful for high density integration. And also, additionally, you may want to put your input and output pins over here at a certain height, such that when you route the two cells next to each other, all you need to do is basically just put a simple horizontal line, and that will ease your routing job. Okay. So these are just some of the flavors of standard cells that you may find in practice. You can have either a lot of these diffusion contacts, or you have basically silicided diffusion. People also put silicided layer on top of this diffusion as well as on top of the poly. But what I want to now show, this is now the layout of the two input NAND gate. So you clearly identify the PMOS transistors basically over here. So you have one PMOS connecting, this is the VDD, this is the output, this is the another PMOS that's controlled by this gate signal B, and then you have two serially connected NMOS. So you have the common ground over here, and then that's this point. And then you have the drain of this transistor controlled by this A is shared with the source of this transistor, which is controlled with this gate signal B, and then finally you arrive to the output over here. And again, you have all this nicely aligned such that when you put the cells together, everything fits nice and snug. So you can put them together. So now, what you really need to learn here is if you have really complex cells. Now the question is, in order to achieve the highest integration possible, what would you like to have is basically this, this following strategy. So what you would like to have is continuous strip of diffusion for the PMOS, and then continuous strip of a diffusion for the NMOS, such that when you connect the transistors in the pull-up and pull-down network with the gate signals, all you need to do is basically just put vertical polylines that correspond to your gate signals. And in this case, you can achieve much higher integration density than if you have, for example, to split the well in one case and then basically have all this space unutilized. So now what you're going to see is that using this graph methodology, how we can really systematically arrive to a solution for standard cell design that has all these nice uninterrupted diffusion areas. Okay. So this is a common strategy that we've already seen earlier in the class, that people use this sort of in constructing standard cells and layout in general. It's sometimes useful just to sort of figure out the relative positions of all these objects in layout, and then use this simplified stick diagram type of representation, and then just throw this in the tool that has all these algorithms that we are going to explain under the hood, and you eventually get automatically generated standard cells. There is a number of industry tools that actually do that, like for example Cadabra, that's a liquid standard cell generator. What it does is basically you just say, here's my schematic of my NAND gate, give me the layout. And you push a button, get the layout instantaneously. If I want to change my W and for the transistors, you get again a new layout. And this is what basically is the strategy in majority of cases in digital circuit implementations. You have all these standard cells with various flavors. Now the thing is, for example, if you put a standard cell of your unit size inverter, then you have a problem when your fan out is too large. And to accommodate that case, you typically have a variety of sizing factors for a given function. So for example, you have 1x inverter, 2x inverter, 4x, 8x, 12x, and that's about like the number they go up to, like 12x, eventually 16x drive capability. And the same thing you have for all the other cells, NANDs and so on. So that when you do your synthesis, logic synthesis, then you can basically pick out which of these cells is the most suitable for the environment of your design. So basically, if you have a large fan out, you're going to use the stronger cell and so on and so forth. And then you can do all the routing at the top level for that. So now we are going to use logic graphs over here and introduce some definitions. So let me go back to this example that we already did so I can explain you what's going there. So now we will introduce a notion of path. And a path is basically trajectory that goes starting from a certain node. A path goes through all the edges of the graph. So it visits every edge exactly one time. So if you have those conditions satisfied, this is called Euler path. So example of an Euler path is, for example, you have, let's start from ground. So you have B, you have C, you have D, and then you have A. So you go around through this graph and visit each of the edges exactly one time. So this is called Euler path. And again, there is a number of Euler paths you can identify here. So you can, for example, go B, C, D, A, or you can go in the reverse direction. You can go A, D, you can go either B, C, or you can go A, D, C, B, and so on. So now, what this tells you over here, the sequence of these edges actually tells you arrangement of all these gate signals for your vertical diffusion strips, right? And so in this case, you would have, for example, implementation of a NAND pull-down network, and then you have certain way in which you order all these diffusions. So A, D, B, C, or you can have C and B. So you can basically play around with this arrangement until you find the best solution for the highest layout density. So the goal here is basically, so the next step now that you understand the Euler path, the next step to find the Euler path with the same sequence in the pull-up network. So if you're able to identify Euler paths in the pull-up and pull-down networks, what this means is that you will have the same sequence of gate signals. So when you have the same sequence of gate signals, you can just route simply vertical poly lines and connect all your gates, maximum layout density in an uninterrupted diffusion, and that's the end of the game. And this Euler path that exists in both pull-up network and pull-down network is called consistent Euler path. So you have Euler path that travels through all the edges, and you have consistent Euler path that's basically the Euler path that exists in both pull-up and pull-down network. So let's identify a couple Euler paths over here, and maybe I can draw this again and this slide so we can. So if this is my pull-up, pull-down network, so then I have my A. So then I have node I, and then I have B and C over here, and then I have ground, and then I have D. So that's my pull-down network.
Could you explain again what's the meaning of the uninterrupted diffusion area, the concept?
The meaning of the uninterrupted diffusion area is basically to allow you to have the highest integration density possible. So if you decide, for example, to have horizontal MOS transistor, and then you have to basically implement a couple of these NMOS transistors in this manner. You can only grow horizontally. You can't use the vertical dimension. So if you're able to sort of arrange these signals in a way that you can have all of these diffusions shared, that basically reduces the width of your standard cell and increases your layout density. So this is, for example, better than the case if I identify, for example, this transistor M1, this is transistor M2, and this is transistor M3. So what happens over here is basically that you not only have uninterrupted diffusion to reduce your area, but in addition you have shared source and drain regions. And you can avoid all these contacts. So you have to have some extra space to allow contacts. So let's assume that we can't do this over here. So what you have is basically then M1, which has to extend a little bit to form contacts for the source or drain region. And then you have to sort of make a break a little bit. And then you have this M2. And then again, you have to create some contacts. So the penalty that you pay in area, you basically have all this contact penalty plus any extra space over here, which results in the overall wider standard cell than in this case. So the goal is to minimize the width and sort of achieve the highest compaction in area so that you can have the best density. Okay. So now let's put together this pull-up network. So if blue is pull-down, red is pull-up network. So this is PMOS, and this is pull-down is NMOS network. So for this guy, we had another node over here, J, and we had node K, and we finally had node X. So we connect this one through D. Then we have A, and we have then C, and we have B over here. So now let's identify some of these Euler paths. So let's say, let's first search through the NMOS network. So we've identified already a couple through here. So we basically said that we can go B, C, D, A. Or we can go A, D, B, C, if you just go into the reverse direction. Now we can also do D, A, B, C, and so on. You can just carry this on. So let's now do the same thing for the PMOS. So for the PMOS, let's see if we can do B, C, D, A in the PMOS case. So if you do B, C, we can do it, right? So in the PMOS, we can do B, C, A, D. So that won't work. These two are not consistent. So let's try A, D, B, C. If you go A, D, we are stuck again, right? We can't even form Euler path that starts with A and D. So tough luck. So how about D, A? So now we have D, A, C, B. No good either. So now let's try to see if we can match this in the pull down. So we have basically D, A, C, B. Yes, that's the winning combination. So D, A, C, B. So now if you can do this, here's what you have in the layout. So you basically have, let's see, this is your, let me use the colors again. Let's assume this is our PMOS network. So this is our PMOS. And then we have blue for the NMOS. Okay. So now what I know is I can do these diffusion strips, and then I do DACB. So if this is my diffusion that corresponds to D, then I have A, C, and B. So now we can figure out also the nodes that correspond to these diffusion lines and the sharing of source and drain regions. So if this is my, this is all, so that's the layout. And then now let's see the PMOS going between D and A. So you start with X over here. Then you go between D and A, you have node K over here. Then you go between A and C, you have VDD. And then finally you have between C and B, you have J. And then finally between, after B, you have K over here. So for the NMOS, you go similar way. So you basically start with D. So you have over here, you have ground. Then you go up between D and A, you have X. Then between A and CB, you have I. Between C and B, you have ground. And then you have I again. So all you need to do is now basically connect all these source and drain areas. For example, you can have contact over here, connect this K. Then you have contact over here, connect this I. And then you have X. And then you finally have, that's it. And then you basically just have ground and VDD, which is basically already implemented over here. You remember that VDD is a stripe going over here, right? You have huge VDD stripe over here, and then you have a ground stripe down here. So this is automatically connected, and then you finally have your standard cell layout. Basically, you may need, so you can almost do this all in one metal layer. You may need maybe additional metal layers if you want to connect all these signals, but if you bring them from the bottom, then you don't even need to spare an extra metal. So that's basically the strategy, how you can create the highest density layout. And this is really valuable. People at companies would really like you to be able to do this. Everybody clear? Mm-hmm.
One more question. So the example in here always assume the same W for all NMOS and for all PMOS.
Correct.
Common practice, or people want to scale those pins so that they're different?
That's a great question. So this is basically, the question is, now we obviously assume the same W here because we had the same width of this diffusion stripe, and that's correct. In practice, it is getting more complicated, but basically this is the principle that you use to have this all diffusions uninterrupted, and I will come back to that different W in a second. I have illustrations for that, for the layout. But you are correct. We will come to that in a second for the propagation delay analysis when we have to consider different sizing. How do we size all these things such that we have the same pull up, pull down, and things in general? Yes, you have different Ws, but this is the principle. Everybody clear with this? All right, good. Should start interviewing now for jobs. Okay, so let me do now look at one more example over here. So this is a little bit simpler function over here where we identify logic graph for this function over here, C times A plus B complement. So equivalent graph representation over here is you have X and I, so you have transistor C, A and B in parallel. Then you have extra node over here in the isolated region. You connect to VDD and X for the pull-up network. So now what you do here, there's two versions of this C times A plus B. So let's see the ordering of ACB over here. So ACB, so let's see, what was this? ACB, PMOS doesn't work, right? So if you do NMOS doesn't work either, right? Pull-up network. Let's see. CBA. Okay, CBA wouldn't work. Let's see. ABC. Seemingly ABC worked, but I don't think so. Let's see, where is the bug? CAB? ABC works, correct. ABC, yes. ABC works. ACB doesn't. Okay, let's see. ACB for the pull-up and ACB for the pull-down. I think this pull-up and pull-down is reversed here, right? Because if we have uninterrupted pull-down ACB, right? Pull-down is blue, ACB. We can't have ACB. ACB can be in the pull-up, but ACB cannot be in the pull-down. Anyway, this is basically the case where this breaks, when you don't have a consistent Euler path for a certain combination. So you have just to continue searching, as we did in the previous example, until you find a consistent Euler path such that you have uninterrupted diffusion strips over here. And yes, actually this is correct, because this is diffusion for the NMOS. PMOS is valid, NMOS is not. So let's go over this again. ACB. So we have ACB for the PMOS. ACB doesn't work for the NMOS. And exactly this is where you have this situation where you have to split the diffusion area, as the question that you just raised a moment ago. And over here you have nice uninterrupted continuous diffusion and the highest density. Okay. All right, good. So this is Euler path over here, consistent Euler path A, B, C for the PMOS, and then A, B, C for the pull-up. One more example over here. It's basically more of the same. You have equivalent graph. You have A and B in parallel. You have D and C, and same thing. You add nodes to the isolated regions, and you connect to VDD and ground, crossing edges exactly once. Here's another example of a function AB plus CD. I think this is the one similar to this one. So basically, you construct a logic graph for this one. So you have AB plus CD bar. So you have AB or CD, and then you have all this intermediate node. You construct the PMOS, and then you have this sequence ABCD for the correct Euler, consistent Euler path. And it's not quite visible in this slide. So you basically just go in the pull down. You have vertical pull down. So you have A, you will go B, C, and D. And then for the pull up, you again go A, start from here actually, A, B, C, D. And then you have this nicely lined diffusion that are continuous for both PMOS and NMOS. You can just route vertical stripes. And if you create this stick diagram, throw it into a tool, automatic layout. Okay, so this is a strategy now to cope with extremely wide transistors. So you have basically a situation when you can have real requirement for a really wide transistor, and in this case, if you just like use really wide diffusion, then you will have, first of all, have a lot of contacts that creates a lot of diffusion capacitance. But a better approach and oftentimes used is to have this multi-fingered configurations. And this is really, if you have access to some of the standard cell libraries, just go open, for example, 1x buffer and open 8x buffer. And you will see exactly this situation. You have fingered implementation of the same transistor width. So what happens here is basically that you eliminate a lot of these contacts, and you have consequently less diffusion capacitance. So you have better performance out of your device. So the properties of all these gates that we've just discussed are high noise margins because VDD and ground are your VOH and VOL signals. There is no static power consumption because you are either at VDD or ground in steady state. And under appropriate sizing conditions, which is what we're coming to next, they have about comparable rise and fall times. I think this is just reiterating all of this that we've learned so far. High noise margins, ratio-less devices. This is for DC analysis, basically, that you always have VOH is equal to VDD, VOL is equal to ground, regardless of the size of your transistors. You will eventually, it will take some time, but you will eventually pull up to VDD or pull down to ground. DC-wise, you have always signals that don't depend on the ratios. In steady state, you always have conductive path to either VDD or ground, so you have low impedance output, which is really good for noise robustness, and it's very good against the crosstalk and those kind of noises. You have extremely high input impedance because no current flows through the gate, and there is no path in steady state between power and ground because you are either at VDD or ground, so no static power dissipation can exist when your VDS is equal to 0. And now we will see how we can cope with propagation delay, that we understand all these DC characteristics. So let's now begin this delay analysis, and we will finish that next time and go into logical effort. So this is a standard methodology that we've been using so far in the class. So we use this switch delay model in which we represent, to a first approximation, we represent each transistor as a serial combination of a switch, ideal switch, and a resistor. And you know that this switch closes for the NMOS when A is equal to 1, and for the PMOS when A is equal to 0. So here are some of the models for delay calculation purposes of the gates that we analyzed so far. So you have a simple inverter, you've seen this already. You have pull-down resistance through the NMOS network. You have pull-up resistance to the PMOS network. And you have the load capacitance that is from the intrinsic load and from the fan-out load. Then you have a NAND gate. In the NAND gate, you have basically serial combination of these two transistors, and you have parallel combination of the two PMOS. For the NOR, you have just the equivalent situation. You have parallel combination of the pull-down and serially ordered pull-up devices. Now you see that you have also this intrinsic capacitance. So this complicates analysis a little bit, but we can still use the same engine we are familiar with, the Elmore delay analysis, to figure out, at least to a first order, what would be the parameters that affect our performance. And most of the times, for the first cut sizing of your gates, you simply ignore this intrinsic capacitance, because they say, well, let's worry about it later. It's not really dominant. Let's try to figure out the dominant factors that contribute to my delay. And so that's the idea. That's what we are going to do next. So now the first realization that you make is, unlike inverters, where we have simple device, pull up, pull down, all I need to care about is make the pull up and pull down delays about equal, I'm good. But over here, you have much more complicated situation, because input pattern affects the delay. You can have, for example, for the PMOS, you can have only one PMOS pulling up, or you can have both PMOSs pulling up, in which case you will complete your transition twice as fast, because you have parallel combination of the two resistors. Your time constant is RP over 2 times CL. If only one input goes low, then you have 0.69 RP times CL. And now for the high to low transition, you need both inputs to go high. And in that case, you have 0.69, and then you have serial combination of these resistors. You have 2 times R and CL. And now this gives you sort of first order estimate of the sizing of these devices to make sure that you have equal pull up and pull down transition. And you always need to budget for the worst case delay. For the worst case delay, for the PMOS, you have only one transistor conducting. That's the weakest you can do, the worst you can do. And for the NMOS, you always have to have a case where both transistors are simultaneously turned on and pulling down. So that's the worst case delay. And we will continue with this next time, and also talk about project in a little bit more detail. See you on Tuesday.